Hello friends, after electrostatics and capacitor, we start the new chapter, current electricity. This chapter is first introduced in the 9th standard, then 10th and 11th, and now is in 12th standard. As we go from 9th standard to 12th standard, the difficulty level of this current electricity, phenomenon related to current, or the new devices, new instruments based on electric current are introduced year by year. Now the current electricity. First we start to revise from the meaning of current. Current is a simple phenomenon. It is a simple physical quantity, very easy physical quantity. It is a fundamental physical quantity. Current, electric current, or simply the current. Current means flow of electrons per unit time is called as the current. Flow of electrons per unit time. So I am writing simply flow of electrons per unit time. Here, suppose the one electron is flowing. Let E be the charge on electron. One electron is there, so 1 E divided by time. Suppose there will be the two electrons are there, then 2 times of E means charge on electron is 1.62 into 10 raised to minus 19 coulomb. As number of electrons increases, then the total charge also increases. So sometimes we can also mention in this way, charge per unit time means my electric current, or in mathematical symbol, electric current is symbolically expressed by capital A. Charge means charge, that is E is a symbol of charge, and value of 1 E is 1.6 into 10 raised to minus 19. And as the number of electrons increases, then the charge increases. So term becomes Ne divided by T. This is the formula for electric current. I equals to Ne divided by T. And the SI unit is very simple. SI unit of electric current is ampere. After that, the term introduced, that is the Ohm's law. What is the Ohm's law? That we have to see first. Okay, this is a very simple or related to electricity. This is the first law, Ohm's law. And on that Ohm's law, we perform our practical either in a 10th standard or in a 9th standard. Now Ohm's law. The mathematical form of Ohm's law is very simple. That is, V is proportional to I. V equals to some constant multiplied by I, or very simple, some constant. V equals to this constant is R multiplied by R, and that R equals to resistance equals to V divided by R. So the mathematical form of Ohm's law is very simple. Potential difference applied between the two ends of a conductor is directly proportional to the amount of current flowing through the conductor. Potential difference applied across the two ends of conductor is directly proportional to amount of electric current passing through conductor flowing through the conductor. And here R is called as a resistance. Now this resistance is not depends on V and I. The resistance depends on the dimensions of the conductor, means its length, cross section area, then material used for the conductor, then also the temperature of the conductor. Therefore, the Ohm's law statement or new statement, modified statement is like this. So long as the physical state of a conductor remains same. So long as the physical state of a conductor remains same, means physical state of a conductor includes what? Dimensions, material, nature of material, and the temperature. These things are remain same. Potential difference applied across the two ends of conductor is directly proportional to amount of current flowing through conductor. So the first two questions for today's lecture are: define current, write its formula and SI unit. Okay, the question is define current define current, state its formula and SI unit. This is the first question. And second question is state Ohm's law. These are the two questions up to this part. Everyone note down these two questions for a homework. Now, in 12th standard, we start the current electricity with some laws. Okay, that are very famous laws. That two laws are there. But before starting that two law, just we see some terms, some important terms related to that two laws. Suppose this is a one conductor carrying a current. Means from this conductor, some amount of current is flowing. I will say I1 amount of electric current is passing through the conductor. One more conductor is there. No matter both the conductors are made up of same material or different material, their dimensions are same or not. Just we see here or concentrate here how much amount of current is flowing. From a first conductor, I1 amount of current is flowing. From second conductor, I2 amount of current is flowing. There is a one more conductor, I3 amount of current is flowing. One more conductor, I4 amount of current is flowing. One more conductor, I5 amount of current is flowing. Let there be the 5 or there will be the n number of conductors, but here in drawing, in diagram, we are showing the 5 conductors. Okay, there are the 5 conductors from which the I1, I2, I3, I4 up to I5 amount of electric currents are flowing. See here, the first conductor carrying current I1, second conductor, third, fourth and fifth conductor, all the conductors are meet at a one single point. Are you getting the point? All the points, all the conductors are meet, are intersect, are joined by one single point. That single point is called as the junction. Everyone getting this meaning of junction? Two or more than two conductors meet at a one single point. That point is called as the junction. Two or more than two conductors meet at a one single point. That point is called as the junction. Okay? Here all the conductors are meet at a one point. Let O be the point, and this point O is called as the junction point. Point O means the junction point, because here all conductors are meet at a one single point. Now the Kirchhoff's law says that algebraic sum of electric current. The word is what? Algebraic sum of electric current at the junction is equal to 0. This law, this statement is the Kirchhoff's first law. This is also called as the Kirchhoff's current law. The statement is very simple. Algebraic sum of electric current at the junction equals to 0. Here the current is, remember, current is a scalar type of quantity. Whenever there is a sum of scalar quantity, at that time you take the algebraic sum. Okay? Here we are taking the algebraic sum, but because current is a scalar, someone says so. No, the current is vector because there are the directions are shown. No, there are the specific direction for electric current, but it never follows the laws of vector addition. Therefore, electric current is a scalar type of quantity. Everyone remember this. Okay. Now, the current I1, current I5, current I3. Okay. Then the current I2 and I4. If you observe the direction of I2 and I4, I2 is away from junction point, I4 is also away from junction point. I3 approaches the junction point, I5 approaches the junction point, I1 approaches the junction point. So I am writing here, these are approaches junction, and these are leaves the junction. Now, then as per the Kirchhoff's sign convention, the currents which approaches the junction are treated as positive. Therefore, all are treated as positive. And the currents which leaves the junction, these are treated as negative. So my equation becomes like this. It is very simple equation. I1 is my positive because it approaches the junction. Then next current is I2. It leaves the junction, so it is minus of I2. Then I3 approaches, so it becomes a positive. Then I4 it leaves, so it is a negative. I5 approaches, so it's a positive. Okay. The algebraic sum of electric current at the junction is at the point A is at the point O is how much? It is a 0. Here how you decide these two currents are negative? Because that two currents are leaves the junction, so they are treated as negative. The remaining currents are treated as positive because they are approaches the junction. Means, or if I write simply this equation, I1 plus I3 plus I5 equals to this I2 comes to this side, I3. I4 comes to this side, it's a plus of I4. Means from this we also conclude that currents approaches the junction because these are approaches I1, I5, I3. Current approaches the junction equals to current leaves the junction. Means it is what? Total current. Total current or current approaches and current leaves both are same. Means there is a conservation of not a current, because current means what? We already studied current means flow of charge per unit time. Means there is a conservation of charge takes place. Therefore, Kirchhoff's first law is called as a current law, but Kirchhoff's first law is an example of conservation of charge. Everyone remember that. Now, just we revise what we study in the Kirchhoff's first law or Kirchhoff's current law. First, we see the meaning of junction. Two or more than two conductors carrying current meet at one single point is called as a junction. Current approaches the junction treated as positive. Current leaves the junction treated as negative. And the Kirchhoff's first law is algebraic sum of electric current at the junction is treated as negative. From that, current is a scalar. Here current approaches the junction equals to current leaves the junction. From this we conclude that current is a conserved thing, but current means flow of charge per unit time. Therefore we say that Kirchhoff's first law is an example of conservation of charge. Okay, is it clear? Then write down one question for homework. State Kirchhoff's first law, comma, its sign convention and state Kirchhoff's first law, its sign convention, full stop, and Kirchhoff's first law is an example of conservation of dot. Okay, in this way we can write the answer of third question. Now we see the next law. It is also very simple. After the Kirchhoff's first law, we see the meaning of junction. After that, we see the Kirchhoff's second law. What is the Kirchhoff's second law? That we have to see first. Kirchhoff's second law. In a Kirchhoff's second law, this is also called as the voltage law. Kirchhoff's second law is called as a Kirchhoff's voltage law, simply the voltage law. Second law or the voltage law. The first law or the current law, the same way Kirchhoff's second law or Kirchhoff's voltage law. In this Kirchhoff's voltage law or Kirchhoff's second law, there are the two physical quantities are introduced. One is EMF and potential difference. Okay, PD means potential difference, and potential difference is given by mathematical form or given by formula B equals to IR, and EMF means electromotive force, means my EMF. Okay, is it clear? Now we see the Kirchhoff's second law. First we start the Kirchhoff's second law. Again, potential difference is a scalar type of quantity. EMF is also a scalar type of quantity. Now the second law is a very simple. Kirchhoff's second law is very simple. Just we see what is the statement of Kirchhoff's second law. Algebraic sum of potential difference and EMF. Potential difference and EMF. Okay, at the closed loop. At the closed loop is 0. Now we see. Just I introduced the potential difference. Full form of EMF is known. Then what is the meaning of closed loop? Just in the previous law, there is a junction is a new word. In the same way, closed loop is a new word. Now we see what is the meaning of closed loop. Okay, closed loop, its meaning is very simple. Any closed conducting path, any closed conducting path through which current is flowing, that is nothing but closed loop. Any closed conducting path, this is my conducting path or this is my closed path. If the current is flowing, then it is called as the loop, current loop, closed loop in this way. Okay. Now we see the mathematical form. Potential difference and EMF across any closed loop equals to 0. Algebraic sum of potential difference plus EMF equals to 0. Just I am going to one circuit. And from this circuit we can easily study the Kirchhoff's law. Okay, it will be very easy. I am taking the example from the textbook. Now this is a symbol of resistor. There are 5 resistors. Let R1 is a 1 resistor, R2 is a 1 resistor, R3 is a 1 resistor, R4 is a 1 resistor, and R5 is a 1 resistor. There are the 2 cells of EMFs, E1 and E2. This is my positive terminal of the cell. This is negative terminal of the cell. This is the positive terminal. This is the negative terminal. Now the current is flowing. Now what is the direction of electric current? It will be very simple. Current flowing in this direction. Current flow from positive to negative terminal. Therefore this is my I1 amount of current is flowing. This I1 amount of current reaches up to this point. From this I2 amount of current is flowing. Both the currents are meet at this point, and from this point, how much amount of current is flowing? It will be very simple. It is I1 plus I2 amount of current is flowing. Okay. Now again this I1 move to this side. Again this I2 move to this side. Are you getting the simple diagram? This is a very simple diagram. Now, there are how many closed loops that we have to see first? How many closed loops are present here? Just I am labeling it. This is an A, B, C, D, A. This is a one closed loop. Yellow color is a one closed loop. Just I am mentioning here. A, B, C, B, A. This is the one closed loop. Now the second loop is. Okay. Now we will label it. Second closed loop is B, M, N, C, B. This is my second closed loop. And the third closed loop is A, M, N, D, A. A, M, N, D, A. Okay? To mention or to write or to express Kirchhoff's second law in a mathematical way, we have to select only two loops. Okay? So, we start from the first loop A, B, C, D, A. What is the mathematical form? Now, to study the mathematical form, just remember only two sentences. These are nothing but the sign conventions. In the direction of current, potential difference is negative and vice versa. Means opposite to direction of current, potential difference is positive. This is the first sign convention. Second sign convention. Negative terminal to positive terminal of cell. EMF is positive and vice versa. Okay? Now we start to write. Using this sign convention and apply these two sign convention for the first closed loop. Closed means A, B, C, D, A. Any closed path through which current is flowing. The current is flowing in this way. Now we start to A to B. A to B. Is there any cell between A to B? No. There is only one resistance. Okay. Potential difference is given by formula V equals to IR. So current flowing through R1 is how much? I1 multiplied by resistance R1. So its mathematical form becomes I1 R1. But in the direction of current, potential difference is negative. We are going A to B, so we are tracing the loop in the direction of current. So potential difference is negative. Now B to C. Next part is B to C. B to C. Again we are tracing the loop in the direction of current. So resistance is what? R3. Currents are I1 plus I2. So minus R3 in bracket I1 plus I2. Then C to D. C to D. Again we are tracing the loop in the direction of current. So again there is a negative sign. Minus I1 R4. And D to A, there is no resistance. Sorry, there is no resistance. Means there is no potential difference, but there is a cell. Means we are considering the EMF. And negative to positive terminal, EMF is positive. What is the EMF of this part? Is a E1. So my condition becomes plus E1 equals to 0. Then the same way for second part. B to M. B to M. B to M. Current is how much flowing in a Vm? I2 amount of current. The resistance is how much? R2. So I2 R2. Now we are tracing the loop opposite to direction of current. So potential difference is positive. Then M to N. M to N. We are tracing M to N. Means first positive terminal, then negative. So my E2 is negative. Then N to C. N to C. Opposite to direction of current. So it becomes minus of I2 R5. Then C to B. This is the last one. C to B. C to B is opposite to direction of current. So R3. It is a plus. R3 in bracket I1 plus I2 equals to 0. Okay. Here the algebraic sum and potential differences are across any closed loop equals to 0. This is the statement of Kirchhoff's second law. Sign conventions are very simple. If you trace the loop in the direction of current, potential difference is negative. If you trace the loop against the direction of current, then potential difference is positive. If you trace the loop positive to negative terminal, EMF is negative. Negative to positive terminal, EMF is considered as a positive. These are the Kirchhoff's sign conventions, and using that sign convention, we can write the equations. Okay, and from that equations, we have to find out the values of I1, I2, I3, resistances, and all the things. Okay. Now, in this Kirchhoff's second law, potential difference and EMF are there is a means their algebraic sum equals to 0. EMF, how we find out the EMF? EMF is nothing but, it will be very simple. EMF means work done or net charge is my EMF. Now the charge is already constant, means work is constant. Work is again one form of energy. So Kirchhoff's second law is an example of conservation of energy. So write down the next question. State Kirchhoff's law and its sign convention. This is a one question. Next question is that Kirchhoff's second law is an example of conservation of dot. Today I am providing you the one question related to electric current definition, formula and its assignment. Second question, method statement of Ohm's law and its mathematical form. Then third question related to the Kirchhoff's first law, and now the last question related to the Kirchhoff's second law. Just pause this video. See, are you clear this term or clear the sign conventions or not?